Good morning, everybody. Welcome to another sunny morning of Chem 1105 with your host, me, Dr. White. By the way, Rain, good morning to you. I hope you're all ready for an exciting morning. All right, here's the game plan for this morning. First of all, because a lot of you have problems with mold problems on test two, I'm going to do two of them today, or actually, you're going to do them, and then I'll do them, and it'll give you practice. You will need this knowledge. Guess what? On test three. Let me remind you before I do this, don't forget, Thursday, test three after our lab in class will be like test one and two. And test three, as I posted, will cover gases and solutions, which I finished yesterday. Uh, Quick question, Jada? Yes, I'm getting to that. You're ahead of me. All right, next, after the mold problems, we'll just do two. I think that's enough to give you some practice. I'm going to go through the gases problem set. After I go through the gases problem set, I will go back, well, not go back, continue with acids and bases, because there's stuff I need to cover that we'll be doing for today's lab, which deals with, are you ready for this? Real dangerous chemicals that are acids and bases, including vinegar, ketchup, mustard, wow, and even baking powder. So, anyways, I'll go through that. We'll do the lab, and then I'll say goodbye. And that's today's lab day. Remember the lab amnesty program. Check Blackboard. If you don't see a score, send me the lab. If you sent it once, send it again. I might have missed it. And by the deadline Saturday, by Sunday evening, hold on, dirty lenses. Oh, it works better. My eyes even open more. But anyways, uh, make sure you hand in any labs that you haven't gotten a score for yet, because labs are, yes, 10 points, and you don't want to lose 10 points because you, or 7 or 8, because you didn't hand in a lab. That can drop you sometimes a whole letter grade if you don't hand in enough labs. So please hand in labs. That's why I have my amnesty program. Don't forget a lab's due today. If you have any problems with any labs, you can always come to my office hours Monday and Wednesdays from 5 to 6 p.m. If you need extra help, email me and I'll see if I can squeeze you in. I can set up Zoom meetings anytime, but I have to be free. Speaking about free, uh, let me remind you Monday, Tuesday, Wednesday, Thursday, in the afternoons to the early evenings. I'm teaching at another school. So if you email me in the morning while I'm teaching here, I probably won't get to that email until tonight or the next morning because this is my schedule. But I do promise I will respond to every email within 24 hours or less, usually less, but still, there might be a case where that might happen. All right. I see a question maybe, and I've answered it. So let's get to work. Oh, that reminds me, almost one more thing. Don't forget, if you want 10, yes, 10, 10 bonus points, do the bonus project. Look at the video yesterday. I talked about it, and you should be able to do it to get 10 points. Remember, if you finish it early, email to me. I'll check it and get back to you and tell you, no, this is wrong, this is wrong. You got to change it before you upload it by the deadline. That way, there's no reason if you put in this effort, you can't get 10, 10 bonus points. That's like adding 10 points to any one of your tests. Good thing. All right, let's get going. think on the test I had 5 points or 6. All right, let's look at this problem. I'll help you out a little. And I wrote a G here. I could have written it like that. How many grams sodium hydroxide, NaOH, are in 7.79 moles of sodium hydroxide? Before I let you start, let me go to something you should be looking at. And for test 3, notice 1 mole of a compound equals the molecular weight of that compound in grams. The molecular weight of that compound is the sum of all atomic weights. Again, 1 mole of a compound equals the molecular weight in grams of that compound, and the molecular weight of that compound is the sum of all atomic weights. We're going to do this Winky Dink style. If I haven't mentioned Winky Dink, what that means, give me a thumbs up right now. If you don't know who Winky Dink is, give me a thumbs up. All right. Winky Dink is this little star character that was a great TV show when I was a kid. And you put a piece of plastic on your television set. That was back when we had tubes. And every once in a while I would say, kids, drawing a ladder to help Winky Dink get out of the hold of a ship or other things. Well, we're going to do it step by step. It's also called in education fading prompts. First of all, what I want you to do right here is write down what are you given? What are you trying to find? Again, what are you trying to find? What are you given? Do that now. Ooh, sounds authoritarian. Do it now. By the way, my Y here looks better now. All right, let me help you out. What are you being asked to find? I use a question mark to remind me of that. You're trying to find grams of NaOH, sodium hydroxide. What are you given? 7.79 moles of sodium hydroxide. Now, there's only one number you have to deal with, and that's this. And why don't you fill in what goes here, but first what goes there? Just the units, put that first. I'll give you another 20 seconds to just put the units in where I have the 3 dots. What should go there? All right, let's do this. What goes here is what you're trying to find, which we determined right here, grams of NaOH. How do we determine what goes here and here? Use your good buddy, your good friend. Oh, that was strange. Unit analysis. And how do you use unit analysis? Whatever you're trying to get to goes on top of the ratio. Whatever you're trying to get rid of, we don't want moles of NaOH in our final answer. We put underneath the ratio. And now I'm going to write that in. And where do we get these numbers? From the fact that 1 mole of a compound equals its molecular weight in grams of that compound. And the molecular weight is the sum of all atomic weights. So now we have to calculate that. And how do we do that? Well, it's the sum of all atomic weights. And notice over here, I gave you the atomic weights for sodium, oxygen, and hydrogen. Notice in sodium hydroxide, there's 1 sodium, 1 oxygen, and 1 hydrogen. Hydrogen. And that means 1 times 23.0, 1 times 16.0. Remember, these numbers are on the periodic table. And 1 times 1.01. If you add them up, you get this. Is that the correct number? No. Remember, when you're adding, which we're doing here, you have the same number of significant figures in your final answer to the right of the decimal as the number you're adding that has the fewest significant. 1, 1, 2. Which is the lowest number? Hopefully you picked 1. And now I'm going to let you figure out how do you round that off the 1 significant figure to the right or past the decimal. And the answer is time's up. Keep the 0. That's your 1. Use this number to round off. Is that 4 or less? Yes. So you drop it. So for every 1 mole, there's 40.0 grams of sodium hydroxide. And now if I notice moles divided by moles, because anything divided by itself equals the number 1, guess what? It's time to pick up my calculator. Ta-da! And my calculator gives me the number 3.116 times 10 squared. Is that correct? No. On test 3, just like test number 2 and 1, it will say underneath your name, please use proper significant figures for all calculated answers. How many does this have? 3 significant figures. How many does this have? 3 significant figures. This is an exact number. That's part of the definition. Therefore, my answer should have, by the way, That's an awful looking 3, which is how many significant figures your answer should have. I'll let you round that off to 3 significant figures. And I hope you all got this is equal to 3.12 times 10 squared grams of sodium hydroxide. And that's the skill you should have for test 3. Let's go to one more, and that would be and the question is, if we're on test 2, how many moles are 36.55 grams of water? And I'm going to ask you first, put down what are you being asked to find, what are you given? You have 15 seconds, go. All right, I think that was more than 15 seconds, but I'll give you another 10. 9, 9.2, 9.4, 9.75. Time's up. All right, what are we being asked to find? How many moles water? What are we given? 36.55 grams of water. You also know 1 mole of a compound. This is important information, equals the molecular weight in grams. The molecular weight equals sum of all atomic weights in a compound. And now each hydrogen is 1.01. Each oxygen is 16.0 for the atomic weight. You find that from that. And I'm going to help you out. You fill in what goes here, here, including the numbers. Your turn. And for all of you who can, if you want to make Dr. White really happy, turn on your webcam. That went over good. And when you're done, give me a thumbs up. You don't have to do the math. You just have to set it up. All right, I see a number of thumbs up. I'll give you another 35 seconds to finish up. You don't have to do the calculation in terms of your calculator. Just put the numbers in unison. All right, let's do this. What goes here? Well, what we're trying to get to, the units, and that's moles of water. And now I'm going to use my good buddy, my good friend, unit analysis. Whatever I'm trying to get rid of goes underneath this ratio. Whatever I'm trying to get to goes on top. I can write those in. And where do I get a ratio of moles of water to grams of water? 1 mole of a compound equals its molecular weight. And the molecular weight is the sum of all atomic weights. How do I do that? Water is 2 hydrogen, 1 oxygen, 2 times 1.01, 1 times 16.0. Remember the atomic weights you get from the periodic table. You have to round those off to 3 significant figures. Do the math, add it up. You get 18.02, but for addition, you get the same number of significant figures to the right of the decimal as the number you're adding that has the fewest to the right. You never do anything to the left other than just add it up. And this is 2, this is 1. Hopefully I'll pick 1 as the lower number. Keep the 0, use the 2 to round off. It's 4 or less. So for every 1 mole of a compound, every 1 mole of water, there's 18.0 grams. Now, before I pick up my calculator, notice grams divided by grams equal 1, because anything divided by itself equals the number 1, cancels out. I'm left with moles of water, yay. And now I'll look, and before I do the math, this is 4 significant figures. This is 3 significant figures. Remember, 0 past the decimals, significant figure. And this is an exact number. It's the definition, 1. And therefore, my answer should have 3 significant figures. And now I can pick up my calculator, clear it. Oh my goodness. And my calculator gives me the following number. And it's times 10 to the 0, which is 1. And how do you round this off to 3 significant figures? I'll let you do that first. And the answer is keep the 2, keep the 0, that's the decimal point, keep the 3, use this number to round off. It's 4 or less, therefore I'm going to drop all this. That's 2.03 moles of water. And that's how you do this. Listen carefully. You should know how to do those 2 problems I just did, those 2 for different molecules. Why? Because you're going to need it for test 3. You're going to need it both for a gas law problem and for a molarity problem. If you can't do that, you're going to lose points. So 1, go back and watch the video, which I'll post later today, if you want to see what I just did again. And two, come to my office hour Wednesday night if you need extra help, or stay after lab today if we have time, if you have any questions. But watch the video, practice that. Go back to chapter 5, part 2, and look at those problems with that kind of mole to gram or gram to mole and see how I've done it and the answers. And you practice it. Remember, if you watch me do it, well, that's why I did this. I secretly had you do it yourself. So you see, if you're on your own, it takes practice. All right. I'm going to ask a question. All right. The question will say, are you done? But I'm going to ask you, yes, you felt what I just did was beneficial? No, you didn't. Put down no. And it says, are you done yet? And I'm really asking, did you think what I just did helped you? Well, good. It looks like everybody was helped by that. How are we doing time-wise? Doing good. All right, let's go to the gas problem set, which you should know how to do for test 3 coming up this Thursday. All right, thumbs up, people. Do you see? You should, but I'll still ask you. See chapter 6, gas problem. Thank you. All right, you should know how to go from torr to millimeters, from millimeters to torr, and from atmospheres to torr, and torr to atmosphere is also millimeters mercury to atmosphere and back. What do you need to do for these first 4 problems? You need to know 1 atmosphere, that's ATM, equals 760 torr equals 760 millimeters of mercury. And just to show you, the past students had to memorize that. Notice on test 3, important information, I give you that right here. So let's try one. Let's look at one. How many atmosphere is 740, number 3, 741 torr? What are you being asked to find? How many atmospheres? Remember, ATM is atmospheres. It's not the place where you get money, at least in this course. And what are you given? 741 torr. So we have 741 torr. We're trying to get to atmospheres. What goes on top of this ratio? Yep, atmospheres. What are we trying to get rid of? Torr. That goes underneath. Where do I find a relationship between atmospheres and torr? Oh, look, it's right here. 1 atmosphere equals 760 torr equals 760 millimeters of mercury, which the last one we don't need for this problem. And remember, all 3 of those numbers are exact numbers, which means you do not have to, you do not use those, not have to, you do not use those for determining significant figures. So 741 is 3, my answer is 3, and here's the number you get. And if I were asked another one, how many torr is 1.237 atmospheres? What are we trying to find? Torr. What are we given? Atmospheres. We have 1.237 atmospheres. We're trying to get to torr. Torr goes on top of our ratio, atmospheres underneath. Where do I get those numbers? 1 atmosphere equals 760 torr. These are exact numbers. Notice this is 4 significant figures, which is why my answer is 4 significant figures. All right, moving on. Number 6, if a balloon has a pressure of 658 torr and a volume of 1.894 liters, L is liters, volume, what is the pressure of the balloon if the volume is increased to 5.133 liters? So what are we being given? We're given initial pressure, initial volume, and a final volume, and we're trying to find the final pressure, P2. Now, in the past, students had to memorize Boyle's law, but I'm teaching it different now. I'm testing your chemistry knowledge, not also your memory ability. And here we have Boyle's law. P1 equal V1 equal P2 equal times P1 times V1 equals P2 times V2. P1 is the initial pressure, V1 is the initial volume. P2 is the final pressure, V2 is the final volume. How do you know to use Boyle's law? Good question, thank you. And if we look at the practice problem, notice all you have here are pressure and volume. And one of those variables has changed, the volume. So whenever you have just pressure and volume, immediately you should know, yep, that's Boyle's law. P1 times V1 equals P2 times V2. Now we want to solve for P2, the final pressure. So we have to get P2 alone. Well, how do we get rid of V2? Divide by V2. Anything divided by itself equals number 1, meaning it's gone. Whatever you do to one side, you have to do to the other. I did. And V2 over V2 equals 1 times P2 is P2, and that's equal to P1 V1 times V1 divided by V2. You don't have to, but I like to rewrite it. Good habits, Dr. White doesn't change. I won't. And therefore, I just rewrote this from here. And now, because I took the time, I can put in the values. And I do. Now, before I pick up my calculator, notice liters divided by liters. Anything divided by itself is number 1. That unit's gone. I'm left with torr, which is a measure of pressure, and I'm in the right track. And notice this is 3, 3, 4 significant figures. My answer is 3. And I've given you other ones that you should go back and try on your own if you haven't for Boyle's law. Now, let's look at number 9. And now let's go to number 10. I like that one better. Now, if you burp 86.75 grams of CO2, wow, that's a monster burp, at 545 millimeters of mercury and 34.6 degrees C, what is the volume of your burp? Well, first of all, what are you being asked to find? Volume, which you use the letter V. We're given a weight of the carbon dioxide. We're given a pressure, millimeters of mercury is pressure. We're given a temperature. I put down R for a reason. Why? If you notice you have a gas, you burp gas, CO2, and none of the variables are changing. Listen carefully. When you have a gas and you're being asked to calculate something and none of the variables are changing, you immediately know that's the ideal gas law, PV equal nRT. And if you look at important information, test 3, we have the ideal gas law, PV equal nRT. And there, in the past, I'd have students memorize this. No, I'm giving it to you, but you have to know how to use it. And we have P is in pressure, pressure in atmospheres. V is volume in liters, and I'll always give you a volume in liters if I give you a volume. N is moles. T is temperature in Kelvin. And R is the universal gas law constant, 0.0821 atmospheres, liters, moles K. Now, let me remind you that this is a calculated number or measured number, and this is 3 significant figures. You can find for more, but for this class and all my life, that's what I've used, and it works. So whenever you have a gas and nothing's changing, but you're given some of these, you know to use PV equal nRT, the ideal gas law. Now, what are we being asked to solve for? Volume. Well, PV equal nRT, and we want to find volume, we have to get V alone on one side. How do you do that? Well, how do I get rid of P times V? Get rid of P, divide by P. Whatever you do to one side, you have to do to the other. Now, V equals nRT divided by P. Well, what's N? And if you look, N is moles, but you're given grams. And just like we just did the problems immediately before, which is why I did it, because you need to do it for this problem, we have grams of CO2. We want to get to moles of CO2. Whatever we're trying to get rid of, or get to, I mean, goes on top. Whatever we're trying to get rid of, grams, goes underneath. And where do we get these two numbers in a ratio? 1 mole of a compound equals the molecular weight of that compound in grams. Again, 1 mole of a compound equals the molecular weight in grams. And now what's the molecular weight of CO2? 1 carbon, 2 oxygen. Each carbon has atomic weight of 12.0. Each oxygen, 16.0. 1 times 12 is 12.0. 2 times 16.0 is 32.0. Remember, 1 and 2 are exact numbers. And we add it up and we get 44.0. So for every 1 mole, we have 44.0 grams. Grams divided by grams cancel out. And this is 1 is an exact number, 44.03. So here's 3 significant figures. So I now have N. And if you forget what these letters are, what do? You go back to important information, test 3. N is number of moles. Next, let's do P. P is pressure, but it has to be in atmospheres. Common mistake, student puts 545 in for P. I mark it wrong because it's wrong. P to work and PV equal nRT has to be in atmospheres. So how do you go from 545 millimeters of mercury to 1 to atmospheres? Use unit analysis. Whatever you're trying to get to goes on top. The units go underneath. Where do you get this important information for that ratio? 764 equals 760 millimeters of mercury equal 1 atmosphere. And I'm on the wrong thing. Sorry about that. Now I'm on the right thing. So we're trying to go from millimeters of mercury to atmosphere. Unit analysis tells us what we're trying to get to. ATM goes on top. What we're trying to get rid of, millimeters of mercury, mmHg, goes underneath. And 1 atmosphere equals 760 millimeters of mercury. And that's where we get those numbers. These are exact numbers, three significant figures. Next, temperature. Temperature has to be in Kelvin. Kelvin is degrees C plus 273, in case you forgot that. I have that right here, important information. Test number 3, Kelvin equals degrees C plus 273. So temperature in Celsius is 34.6 plus 273. Notice you get the same number of significant figures to the right of the decimal as the number with the fewest. Well, 273 is an exact number. The only number you consider is 34.6, one past the decimal. And this is the actual answer. So let's take a look. I have N. You'll be given R. I have T, I have P. Put them in, and I get the number. Oh, wow, 69.4 liters. If you could ever, which you can't, burp that much, 86.75 grams of CO2, guess what? That would be the same as almost 35 2-liter pop bottles. I don't think your lungs are that big. No, they're not. But it's fun to theorize. And that's how you use PV equal nRT. Now, don't forget, PV equal nRT tells you when to check your tires. And in winter, what happens? The temperature drops. So if we have PV equal nRT in your tires, R, N, and V stay the same. The volume doesn't change, the moles don't change, and the universal constant R better not change. So if the temperature goes down and this side has to equal this side, then the pressure goes down. So PV equal nRT tells you temperature goes down, pressure goes down, you better check your tires. In summer, gets hot. Hopefully not too hot this summer, not like these West Coast. Well, in your tires, there's gas, air, or nitrogen, and PV equal nRT. And since again, volume, moles, and R should be constant, when temperature goes down, wrong way. When temperature goes up, the pressure goes up. So temperature up, pressure up from PV equal nRT, which means keep an eye on your tires so they don't blow up. And if you look at number 11, I have one with an actual tire, and you should look at this also on your own. If I look at the clock, I think let's take our break now. Let's take a 5-minute break, come back at 9:50, and I'll see you in 5 minutes. Oh no, I'm late. I'm late for a very important date. You know where that comes from? Time to get going. All right, there's one thing more I'll talk about where concerning gases, because it's so pretty straightforward. I didn't even put the problem set for it. And that's Dalton's law of partial pressures. The total pressure of a mixture of gases equal the sum of the partial pressures of each individual gas. And the partial pressure is the pressure of a gas in a mixture that if we're alone, it would be that pressure. So that's Dalton's law of partial pressures. P total equals the sum of all partial pressures. That's why I have P1 plus P2 plus P3 and so on up to Pn. If you had five, you have P4 and 5. And let you try and do a problem since I don't have one in the problem set. All right, let me make sure you can all see that. And the answer is you should. But I'll ask thumbs up, people. You see my whiteboard? Thank you. All right, this one's for you to do. What is the pressure of a mixture of hydrogen, nitrogen gases? The hydrogen partial pressure is 451 torr, and the nitrogen partial pressure is 111 torr. And let me just remind you, Dalton's law of partial pressure. P total equal the sum of all partial pressures of a mixture of gases. With that, have fun. All right, I think most of you are done. If not, I'll give you another 10 seconds. Go. 9.2, 9.4. Time's up. Quick watch there. All right, what are we being asked to find? The total pressure. What are we given? The partial pressure of hydrogen is 451 torr. The partial pressure of nitrogen is 111 torr. And P total equals the sum of all partial pressures. In this case, it's hydrogen plus nitrogen. And if we put in the numbers, there's none past the decimal, so I have, make sure I added correctly. I think I did, but you never know. And that's how you do it. That would be the total pressure, the sum of all partial pressures. And with that, I'll ask you, are there any questions about gases and the gas problems for chapter 6? I'm looking at down here where I'd have chat. If something pops up when somebody sends to me, I can see it down there. All right. Does everybody feel the same way as Rain? All right. Remember the bicycle story I told you the first day of class. Watching me do them, well, today I had you try it a little on your own, but watching me do it, it's not that hard. I highly recommend you go back, do the practice problems, some of them, at least one with Boyle's Law, one with PV equal RT, and one conversion, so you're ready for test 3. All right. Okay. Today's lab is a little ahead of where we are. So let me, first of all, close something. And let me open something else up. Now, nobody I know, one more ring and it stops. Everybody see my Bluetooth phone? Stop. It did. All right, yesterday we were talking about acids and bases, and today's lab will deal with acids and bases. And acids and bases, and Bronsted-Lowry acid is a proton donor. Proton is H+. Now I'm going to, Bronsted-Lowry base is a proton acceptor. Now I'm going to skip through stuff that I'm going to come back tomorrow. When you have an acid, HA is an acid, any acid. B, guess what, is a base. And they can react. This is called an equilibrium. Double-headed arrow means it can go either forward to the right or back to the left. And what you form are these two, which we call salt. And I'll teach you tomorrow, I'm not going to go through it now, about conjugate acid-base pairs. And I'll talk about strong and weak acids tomorrow, which will also help you with today's lab. Now, it turns out water can react with itself, but it's mainly to the left in what's called dissociation. And you form the hydronium ion and the hydroxide ion. And I'll teach this more in detail tomorrow, but I just want to go through this so you can understand today's lab. And the hydronium ion concentration, there's something called an equilibrium or ionization constant. KW, no, it's not named after me. I wish it was. Every time I see it, those are my initials. But that stands for water ionization constant, or ionization constant for water equals, when you see a bracket like this, that means moles per liter. Oh, concentration. And that's the hydronium ion concentration times the hydroxide. And at room temperature, it's 1, actually it's 1.0 times 10 to the minus 14. And I'll go over this tomorrow. I'm just zooming ahead. Now, important thing, how many of you have heard, oh, your stomach's acidic? Have you ever heard that, or this is basic? Give me a thumbs up if you've ever heard, the term acidic. I see a few of you. Well, we'll get through it. I'll come back tomorrow and go in detail, but let me talk about it. Change view. And acidic has the hydronium ion concentration greater than the hydroxide. Basic has the hydroxide ion greater than the hydronium. Now I'm going to, this is sometimes called alkaline, like your alkaline batteries. And finally, neutral is when both concentrations are the same. For acidic, the hydronium ion concentration is greater than hydroxide ion concentration. I'm going to go over this again tomorrow, but I want to cover it just for today's lab. And when you hear tomorrow's lecture, you'll understand more of today's lab. I'm off by an hour or two in lecture, which in the summer is really good. I assume everybody can see my whiteboard now. For acidic, by the way, this symbol means, in case you forgot, greater than. It's from math. And the hydronium for acidic, hydronium is greater than a hydroxide. For a basic solution, hydroxide is greater than hydronium. And for a neutral solution, the hydronium ion concentration equals the hydroxide ion concentration. Now, to look at these numbers and have to figure out which one's smaller, which one's larger, and all that, that's a lot of work. And it's not easy work. Well, someone came up, and one of these days I got to look up on the internet who came up with the pH. Someone invented a really important scale. And we call that the pH concept. And I'm going to go through this again tomorrow, but we'll need it for today's lab. And the pH scale is a scale of small numbers that are used to specify molar hydronium ion concentration in aqueous, meaning it's in water solutions. And pH is equal to minus the log of the hydronium ion concentration, H3O plus. Relax, take a deep breath, let it out, take a deep breath. Are you all relaxed? It's time for a small gift from Dr. White. Instead of me having you struggle with your calculator to learn how to do what's called logarithms, I'm not going to teach that. I came up with a special gift. And here's my special gift. Watch. If the hydronium ion concentration is 1.0 times 10 to the minus x, then the pH using this formula is x. So an example, if I said, what is the pH if next here is that's better. Well, pH equal minus the log of the hydronium ion concentration. And we're given it right here. So it's minus the log of 1.0 times 10 to the minus fifth. Since this is 1.0, what's x? Well, x is 5 because we're saying if the pH is 1.0 times 10 to the minus x, then pH is x. So the answer here would be 5. And that's how you do pH. Now, here's what you need to know for today's lab. We're going to be doing reactions with certain chemicals. And if you take an acid and you add a base to it, we call this a neutralization because this is a salt. And what happens is when you add a base to an acid, the pH increases. But am I telling you the truth? I don't know. You're going to find out in today's lab. Now, let's look at today's lab. Now, can everybody see doing chemistry with food on your screen? Thumbs up, people. Give me some help. All right, thank you. All right, now, all the kitchen items that you find in your kitchen and supermarket are chemicals. Yep, chemicals. And these the food you eat and the ingredients that you use to make various food dishes are composed of atoms and molecules. Yeah, it's chemistry. And in this lab, you will be investigating the acidity, whether something is an acid or a base of various foods and cooking ingredients. Remember, an acid is a proton donor, a base is a proton acceptor. We measure basicity and acidity by measuring the pH of a solution. Remember, if hydronium is greater than hydroxide, it's acidic. If it's hydroxide greater than hydronium, and why these aren't subscript, sorry about that. That's better. And the pH is an important measurement chemists use to determine the acidity of base of a solution. As I said, pH equals minus the log of the hydronium ion. Now let's talk about pH. This I'll do again tomorrow, but it's important to know. The pH scale, it goes from 0 to 14, never greater than 14, never less than 0. In fact, years ago, at one company, I was managing this large research group, and a chemist who had a master's degree in chemistry gave me a report at all companies before you issue someone in my research group issues a report, the section head has to proof it and approve it. I actually sign off on a form with my name, because if there are any mistakes, it comes back to me. That's my responsibility. Well, he gave me this report, and he measured a lot of important pHs in his research. And after I read it, I said, let's go into my office. I looked at him and said, do you want to be employed here tomorrow? And that got his attention. He said, what's wrong? And I gave him his report back. And I said, never, ever give me a report where you put down pHs greater than 14. At our level, we use what's called a pH meter, and he didn't calibrate it properly. That was the problem. I said, don't ever give me a pH greater than 14. You can't have a pH greater than 14 or less than 0. Next time you do this, you won't be here the next day. I was really upset. Any chemist with a degree should have known better. And he learned his lesson quick. That's the bad side of Dr. White. You never want me mad. I never want me mad. But anyways, if we look at the pH scale, this is one of the most important things I'll teach you this whole semester. pH scale, 14, 0, 7. Below 7, we call this acidic. Your stomach, well, I'll show you in a second. At 7, when you have something that's pH of 7, that's neutral pH or neutral solution. Above 7, we call that basic. So pH can never be greater than 14 or less than 0. When it's less than 7, it's acidic. When it's equal to 7, it's neutral. When it's greater than 7, it's basic. The lower it is, the more acidic. The higher it is, the more basic. Now, when you add a base to an acid, the pH should go up. And there are different types of bases. There are weak ones and strong ones. The weak ones, you've got to add a lot to make it go up. The strong ones, you don't have to add a lot to go up. Now, let's go out on the internet and see if I can find something real quick. No, I don't like this one. Hang in there, sports fans. All right, can everybody see on your, let me make sure I can check. Yep. Everybody see on your screen on the right upper corner, you see those colored bars? Thank you. Now, in the middle, they have this, you have pH 7, pure water. You cannot get pure water from your tap in your house. It's never exactly 7. And I'll tell you a story in a second. Now, if you notice, the lower the number, the more acidic. Hydrochloric acid, pH 0. Now, if we look at vinegar, yes, has an acid, and that's a pH 3. If we look at tomatoes, pH 5. Tomatoes have what's called citric acid in there. If we look at ammonia, which is a strong base, it's pH 12. And there are different things here that have different pH. And if we look, where did it go? If we look here, they've got Coca-Cola at pH 3, and they've got, I didn't realize that, carrots at a pH 10. That's interesting. And water at 7, and certain beverages and cheese at 4. And these are different pHs. Now, today's lab, you'll be measuring pH with what's called pH paper. You stick it in there and you measure, look at a color and compare it to a scale. And with that, it's time for Dr. White's I Found a Good YouTube. All right, everybody see YouTube on your screen? Let's find out. You should. Where are my thumbs up, people? Thank you. Let me maximize this.
Okay, this is the video where we're going to be testing various solutions with pH paper. So you can write down a chart, give it this heading or title, testing pH with pH paper. We've got sodium hydroxide base, hydrochloric acid, vinegar, baking soda, lemon juice, window cleaner, Drano, and detergent. Don't worry about that last row. We actually don't have an unknown. So we're just going to test 8 items, okay? They're in the same position on this spot plate as they were in the chart. We're going to use pH paper like this. It'll change color, and we'll match up the color change with what we see on this color chart here to try to determine exactly what the pH actually is. So let's do the first one, sodium hydroxide base. And when we compare it, we can see here, yeah, that's kind of a 12. Next one is hydrochloric acid. And we got a nice pink to red color, so that's, you know, pH 1, probably, yeah. The next one is vinegar, and we get kind of an orange color for this one. That's kind of a 3. We've got baking soda, and we got a nice green color being produced there, and that's kind of a pH of 8. Lemon juice. And we get kind of like a pH of 3. It might be somewhere between 3 and 4. Window cleaner, which is ammonia. We get kind of a light green color here. It's around pH of 7, but not quite as yellow as what you would see right there. So somewhere between 7 and 8. Then we have Drano. And we get a really dark blue color there, so that's a strong base, pH of 12. And then we've got detergent, and that's kind of like a pH of, well, it's not quite 9, not quite 10, somewhere between 9 and 10.
And if we were in the lab, you'd be doing this acidic food, basic, it's neutralized, and you're going to be adding a base to acidic foods, or at least you'll find out, are they acidic, and see the effect of the reaction of pH when you're adding a base to these acidic foods. Now, first one, in our lab, we have what's called DI water. DI stands for deionized. We actually have filters, special cartridges that take out the ions like calcium and other things from the water. But those cartridges, when you put water through them, affect the water. Now, pure water should have a pH of 7.0. But after going through the cartridges, guess what? Here's the pH if you had measured it. And we've done this, I've done this at EOD enough times, that's about the right answer. Now, let's take a quick Dr. White story. I was asked to solve a problem for a company I was working for at one of our plants, and this was in Toledo, Ohio. And part of the problem dealt with pH, and they used water. And I asked a simple question. Oh, by the way, when you're doing problem solving, never assume, because you could become the first three letters. You don't want that to happen. And the first thing I asked, they're using water and we're dealing with pH, what's the pH of your water? And they had never measured it. And this was in late April, almost summer in Toledo, and the pH was close to 8. That was some of the worst water I've ever seen. But anyways, that was part of the problem, and there's ways of adjusting it. But part of good probleming is never assume. And the other thing, which I was taught by a great mentor of mine, Sid Shapiro, God rest his soul, great man. He was at the end of his career when I was starting mine long ago. But anyways, he used to teach me two things and beat it into my head. We carpooled for a whole year, 40 minutes each way from our home. And that's almost 80 minutes every day. He would drill me and teach me things while we were going home or coming to work. And the other thing he used to tell me was common sense is not common. If you're having a problem with pH and you're using water, measure the pH. They didn't. But anyways, back to our lab. Now, in part 2, you're going to measure the reaction of sodium bicarbonate, baking powder with various foods. I've got a couple of videos here. Let's look at one with video with a rocket. And I'm going to tell you a story about this tomorrow. A very personal story. And fortunately, I don't pay money to have commercial-free YouTubes. So let's see how long. Bingo. I waited long enough.
Okay, take number 3. This time, we've got a mixture of 1 cup vinegar to 1 cup warm water in a 2-litre drinks bottle with our launchpad system here. This time we're putting the baking soda inside a pop stop.
Everybody see the YouTube?
So hopefully that will mean that the vinegar can get inside the pop stop more easily and it won't get wedged in the end of the bottle when it's about to go off, which should mean the gas gets out more easily. Here we go then. So cut a little hole in the pop stop there. We're drying out, we should be able to reuse this actually. Very gently, make sure the inside is dry. We're going to feed our bicarb in the pop stop through the gap. Once we've got a bit in, we should just be able to gently dip it in through, push it on down. Right, now we've got the interesting bits. So put the bottom in the right place, ready to run back very quickly. Launch pads ready with the cork. Here we go, and oh, it actually suspends it. That's a nice feature. Ready? 3, 2, 1. Over we go. Bubbling away nicely. Pop stop looks like it's turned into a balloon. Oh, that's definitely a better delivery method. Look at it go. Oh, that's very frothy. That's very frothy. Whoa! Oh, success!
It's the pop sock.
Right, pop socks forever. Wow.
Do I get the credit for that?
I think you did.
And who said chemistry can't be fun? All right. Now, what he had was baking powder with the acid. Coca-Cola and other soft drinks are acidic, and you have an acid-base reaction. And the specific reaction that's in this procedure with bicarbonate, which I'll show you right now on the whiteboard. We'll talk about this again tomorrow. If I get the whiteboard. And the bubbles you saw in that bottle, which built up pressure so it would blast off, was carbon dioxide. And I'll tell you a great story tomorrow about this reaction and Dr. White when I was about, 6 years old, maybe 7. Well, you'll have to wait till tomorrow for that. And that's what you'll be doing in part 2 of this lab. What you'll do is take some water, put a little of the food to be tested in a beaker, mix it, measure the pH, and observe it. Then you'll add some more, do the same thing, measure the pH, add some more, then add a lot more. And then the chemicals, hold on. You're not using Beyond Lab Z for this lab. Thursday you will, but not today. This is totally from Dr. White. And what you'll do is, if you were in the lab, mix it with orange juice. This should be a separate line. Ketchup, tomato paste, that's dangerous because it stains clothes, so be careful. And lemon juice, mustard, and Coke. And you see I got those connected. Hold on, I got something in my eye. That's better. And what I've done for you, which you would have normally done yourself with the pH paper, the initial pH, say, of vinegar is 1. When you added the sodium bicarbonate, you saw bubbles, and the pH goes to 3. Add some more to 5. Add a lot more. It goes to 7, and bubbles were formed. And I have that for all of the different things you test. Now, next one, you're using sodium hydroxide. Oh, look, 0.1 capital M NaOH solution. That's a 0.1 mole per liter or mole per 1,000 milliliters. Now, this is a strong base. Well, maybe it's not. You'll have to see after you do the same thing. Take some water, take some of the food item, add a small amount of sodium hydroxide, do it again, measure the pH, do it again, and add a lot. And here they're separated, and you'll get this table. And you'll measure the pH. And here the reaction is different acids plus sodium hydroxide. Is this reaction. And you're going to determine, is this really a weaker base than this, or is this weaker than the sodium bicarbonate? And you'll look at that by the greater the pH change, the stronger a base a compound is. Sodium bicarbonate is a base, and sodium hydroxide is a base. And HA is just a chemist's way of saying any acid. And you've got questions to answer. And that's today's lab. You do not have to do anything on Beyond Lab Z for today's lab, but we'll be using it in the next couple labs a lot. So, and it's fun, the next couple labs, what we'll do with that. So that's what we'll be doing. Tomorrow's lab, and I'm about to sneeze. Oh, it's a slow evolving sneeze. But anyways, tomorrow's lab, or today's lab, I will discuss more in detail tomorrow stuff about it, but I wanted to cover it today. And tomorrow's lecture will help you with today's lab. And with that, I'm done. And I get to say, don't forget, hand in the lab that's due today. I'll see you tomorrow. Gang gesund. Don't forget, test number 3 coming up on Thursday. Do the practice problems. Tomorrow, I will go through and do the solutions practice problems. With that, gang gesund. Bye. You're welcome, Rain.